Hello, everybody. We are Team 17 in ME 452, and we are working on the analysis and redesign of a retractable landing gear of a model plane. My name is Tiger, and my teammates are Noah, Winnie, Kara, and Jack.
So the product that we've chosen to analyze is the retractable landing gears used by model aircraft. These are usually used during gliding, during takeoff and landing for the aircrafts. And during flight, they would be stowed inside the structure of the aircraft themselves to reduce drag. On the next slide, we have identified the primary and secondary customers. For the primary customers, they would be airplane enthusiasts, and they would like realistic models that look identical to the actual aircraft themselves. And we expect the production volume to be about 44K per year. For our secondary customers, we think they would be aerospace researchers, and they would need functional models to use for testing in the wind tunnel. And the production volume for them would be about 6K per year. And so next we did the functional analysis for the retractable landing gears. Their main function is to just move the aircraft, and we can separate that into three main functions, which is to support the aircraft, glide the aircraft, and stow the systems inside the aircraft. And so here is an exploded view for our product with all the labels and the numbering, which would be referenced for the rest of our presentations.
So this is our function component mapping matrix, which essentially kind of shows you how each of our main parts of our landing gear actually map to the functions that we require in our FAST diagram. Now, moving on to the next slide, we actually look at how to assemble this. There was basically two main things we looked at. Either building it from left to right, essentially putting down the main plate and then building all of the components on top of it, or building the different sub-assemblies and then coming together. Now, in analyzing this on the next slide, we look at how easy it is to assemble based on these factors. We found that the sub-assemblies first method is much stronger than the left to right assembly and makes a lot more sense.
When we take a look at the bill of materials involved in putting this together, we made a few assumptions. The first was that we're not going to be purchasing everything. Building everything. We're going to be purchasing things that we can find off of the shelf, and more specific parts for this application, we're going to be making ourselves. For example, the wheel for this, we can find off the shelf. The pins we can also find off the shelf. So you see that we don't have any processing or material costs for these. And then also when we get to the end here, we can see all of the fasteners. Those have relatively high assembly costs associated with them. And then they have a small per unit cost as well to buy them. We see that when we put this all together, we have a total cost of $23.23 per unit, and we assume manual assembly at $15 per hour for labor. When we take a look at our DFMA quad chart, we see how the functional importance and the manufacturing and assembly costs of each of these components break down. We have things like the structural plates and pins that hold all of this together, which have relatively low per unit cost, but a high functional importance in terms of supporting the weight of the aircraft. But then when we take a look at things like the servo motor and the wheel, those are expensive, but nonetheless critical. We do not have any parts that are of low functional importance, but high cost. But we do have things like spacers and nuts and bolts that are not quite so functionally important, but are cheap.
So moving on to our product family, we have two variants for our two different customers. Our first are going to be looking at recreational customers, and our second are going to be research customers. And the difference in those needs are outlined on the next slide. You'll see that basically across it, our recreational unit needs to be able to bear impact, decelerate the aircraft, and distribute weight as if a normal landing gear in performance, where both customers are interested in deploying and retracting the landing gear for both of their independent functions. And then on the next table, you can see basically the only differentiating factors between these are those two left and right main plates and the kinetic modules, as we go over in the next one. Are pretty much the same. Interfaces between all components for anything moving is going to be identical as outlined in red there. Our RC users are going to be using those notch mounts, which are a standard for model airplanes, where our variant 2 research users are going to be using that grid mount in a wind tunnel to rigidly mount it and study aerodynamic effects. And for our modules, everything moving in both assemblies is completely identical and is assembled before both of the main plates are affixed, as we outlined earlier. All of the hinge points are identical, and everything assembled up until those main plates is the same.
So pulling our assembly sequence from before, we have created a primary and secondary variant version for the two variants. As you can see here, the two sequences are actually identical due to the fact that the only differentiating part of our product is the left and right main plate. So if we take a look at the next slide, we will see the assembly diagram. As I mentioned before, the only difference is the main plate, and that is actually assembled midway through the product. So some of the parts to the right of that can only be assembled once those parts are in. Therefore, this is the way that the diagram looks. Thank you so much for listening, and that is the end of our presentation.